Yeah,
Custom
okay.
buttons.
All right. So, can we go?
Yeah.
Okay. So, for our project, we worked on predicting stock data using news and prices, and mostly we took NLP approaches, and also a couple of approaches on just sort of numerical methods in trying to estimate the prices of stocks based on prior prices. So a couple of our goals, right, is that we get a stock input like this of prices for certain companies, right? And our goal primarily for this project was to identify these turning points in stock prices. So we see regions of stock prices that are fairly uniform and with certain noise, and then we see these turning points where stock prices change drastically. And these were the turning points that we tried to identify through numerical methods and natural language processing. So here's a couple more of them, right? And basically, sort of right here, right, there's the news. An example of the type of news that we used is something like this, where a GE CEO would announce, for example, that an electric car is a success or was a failure, R&D, or certain quarterly reports and other such things. So the data that we used were mainly financial news articles between January 2007 and December 2008. We scraped mostly data from Reuters. And after removing articles that were just not very useful and articles that basically had no stock tickers, so gave us no additional information, we had about almost 300,000 usable articles in total. And we used historical stock prices from Yahoo Stock to Yahoo Finance, and we took these prices and based on time labels, of course, we put these two data sets together to create a labeled data set of stock prices. So this is the pipeline that we followed, right? So we first aggregated news data using a crawler that we wrote to gather Reuters data, right? And then we also wrote a stock symbol extractor to extract the stock symbols that are mentioned in each of the news articles, and that's basically just a series of regular expressions to identify common formats of stock symbols. And we extracted stock symbols mostly from the first paragraph, because mostly if a news article mentions a stock symbol that is central to the news article, that will appear in the first paragraph or the title. And we also extracted the date so that we can correspond these, we can match these articles up with the stock prices that we crawl. Next, we labeled this data, right? We took stock prices that we got from Yahoo, and based on the date, we basically labeled these articles as either having gone up or down. Yeah.
Can I ask you a question about the labeling? So which time scale are we using for the time labeling?
We're using end of day closing prices just because that's all we can get out of Yahoo. It's significantly more difficult to get a lot more companies just because Reuters publishes about basically every market you can think of. And I mean, you can go to Wharton and you can get New York Stock Exchange data down to the minute, but anything that isn't the New York Stock Exchange, you're out of luck. So we just elect to use a longer scale.
Okay. But my intuition is if you have something like announce some good news, great news during the noon, and then the stock.
No, I mean, I perfectly agree with you. This is the constraints I could get a hold of.
Yeah, and the news articles weren't exactly real time either. So most of the time there was sort of, today something happened, and in general I think the time scale we're using for news articles sort of corresponded with the price data that we used. All right, and then and then we push these through. We push the data that we generate through a set of feature generators. Like I said, numerical methods. We use bag of words and also topic modeling, and we'll talk about each of those soon. And we took all the outputs and we pushed it into a Valpo-Wabbit classifier, which is a fast stochastic gradient descent classifier that Daniel will talk about. That came out of Yahoo Research, and that gave us our predictions.
Alright, so I'll talk about the bag of words model. So the first and simplest thing you could possibly do is you take your articles, you just look at them as a set of words. The trick is that it's not really just the words themselves. You might want to do some transformations. You just can't build an index and call it a feature vector and be done with it. Well, you can. And I'll show you that in fact you can rather easily. So basically what happens is you take the article, I applied some NLP stuff, I'll explain exactly what, and then obviously you turn it into a big giant feature vector, and then you just have to choose how important you want each of those words that appear to actually be. So the first thing, the actual NLP part, was we're saying that the way you can basically look at words is you can either look at the word itself, you might take the word lemma, which means to say, like you take, for example, dogs is just dog, R is B. These are unimportant words, but there are more important ones, trust me. To basically say that these words, they mean roughly the same thing, regardless of their tense, but not necessarily always, which is why we also extracted the part of speech. And this is all just a way of saying that, like, how big should our feature dimension really be? So this will give us our index. And the second, as you probably all know already, is actually how to weight the features. You can weight them, just as indicators of did this word appear in this document. You can weight them based on what is, like, if you looked at the document as literally a bag of words, what's the probability you would pull this word out? And then you might also say that words that appear in a lot of documents really don't mean a whole lot, which is what inverse document frequency is right there. And the approach we took in this is we're kind of looking at, okay, so what if we just use term frequency, and what if we use TF-IDF? Does IDF even really mean anything? And then, so what are the actual results, really quickly? So the idea here is that we're just going to try to predict if the stock went up or down. I can explain later why that's the case, but just take it as is. And what I would do is I would look at, okay, should I use word lemmas? Should I use the raw words? Should I use the word lemmas and the parts of speech? What my regularization should be? Whether I should use TF or TF-IDF? And this is just showing what the best we saw in 2007 and 2008 was. And it's a little bit surprising, in fact, that we did so much better in 2008 than 2007. In fact, okay, so these here in black and here in pink is actually random. If we had just chosen a class uniformly at random, which is, well, it's not a good sign. In fact, it's not really great at all. But I'll show you that things do get better. But the surprising part was that basically all the feature transformations you could possibly think of, they really don't matter at all. Like here you see the TF-IDF versus TF. I mean, if you actually look at the best score out of both of these, they're basically identical, up to like maybe 0.2% or something like that. And the same can be said for how you actually generated those feature vectors. Did you use the raw words, the word lemmas, or the parts of speech? You see slight jumps at best, 1%, really. And why is this the case? Well, I mean, we are looking at stocks, right? And there's a whole school about how stocks actually work. And one of those schools actually says that you have no way of knowing, period, what's going to happen next. So the point is that the market is really noisy. So, anyways. Okay, sorry. All right, so that ends the bag of words part. The second part is saying that, okay, maybe just looking at words is kind of the wrong thing. Maybe the stocks themselves really have all the information that's really kind of useful. So we're just going to say that we're actually going to use an adaptive filter, where our signal is the stock price of a single company. And that is here by EN. And then what we observe is XN, which is the actual signal plus some random noise. And what we want to predict will be the signal at the next time step. The way we're going to do that is with a linear filter. And there's the actual person who should be presenting this, unfortunately having a final right now, so I'll only be superficial in its description. But basically what it really comes down to is we're going to do least squares with the last L time steps. And then how we're going to do that, instead of doing that over and over, every time we see a new data point, we're going to do this in an automated way using stochastic gradient descent. So what this says here is that our weights are going to be updated according to our step size, the error of our prediction, and what our feature vector was, basically the last time step. And this is all the normalized least squares, just because you normalize by the vector. There are various theoretical justifications for this. Most of them revolve around signals that you assume things like stationarity, where you can shift the signal in time. These really don't hold for the stock market, so it's more of just an application to see, does it work at all? And the surprising thing is when you predict the sign, it actually does pretty well. It achieves 70 to 72% accuracy on the next day scale. This one was actually also implemented to actually predict the relative change in price. Relative change being what's the price then minus the price now divided by price now. And the error was on the order of, I guess, 0.1%. And then, perhaps unsurprisingly, you don't really want to look too far back in time. You can make a filter that says, all right, I'll use the last 5 days, but really, it doesn't matter that much. If you actually looked at the actual write-up, you'll see that anything more than 2 days is just going to kill you.
Alright,
Actually,
so the third approach that we tried was, instead of saying we're just going to look at the topic, the TF-IDF features, what if we try to extract topics? So instead of sort of using the vanilla words that sort of appear in a news article, what if instead we try to extract topics from them first and to use those topics as our input to the predictor? So in a sense, what we're doing here is we're considering these topic models, which the one we used was LDA, to be a dimensionality reduction technique on the term frequency matrix. So we take the term frequency matrix and we essentially try to extract topics from them. So what we did was, this is the same thing that Bly did in his original LDA paper. You basically predict the topics given the joint probability, right? And then you take the topics that you got and you put it into a classifier and you train the classifier to minimize the error based on your topic vectors. We ran these topic vectors through VapoWeb's LDA implementation, which uses variational Bayes. We use a mini batch of 512 and an alpha parameter of 0.1, which is fairly standard. And these are some of the examples of the topic vectors that we got, right? We have copyright software, so sort of a topic on technology, a topic on stocks, a topic on, I think it's a topic on sort of medical trials and pharmaceuticals, and then a topic on oils. So the performance of just using the topic vectors for 2007, the best performing classifier was to use 50 topics in 2007, and this bottom line here, which is sort of hard to see, is the random predictor, and you can see that the topic predictor for 2007 significantly outperforms the random predictor. However, interestingly enough, in 2008, it's a different story. This line on top is the random predictor, and in 2008, we did significantly worse than the random predictor. And we sort of said, okay, well, let's look at 2008 and think about why that is. So by the way, 2008 was 200 topics, so we actually required more topics to achieve this level of prediction. This graph right here is the F1 score of the predictions. So we took the components of that F1 score and we looked at the precision and the recall independently. And what we saw was basically that we still had good precision in 2008. In that the pink line significantly still outperforms this yellow line, which is the random predictor, most of the time. Right? But we had very horrible recall. I think the yellow line here is difficult to see. It should be around 0.5 because we're predicting randomly. And that the recall was significantly worse for the 2008 predictor. And to sort of dive a little bit deeper into this, these were the topic intensities per topic, the average overall of the documents. And these 50 topic intensities had a standard deviation of about 0.004. But when we went to the 2008 200 topics, these had a standard deviation of about 0.0005, which if you think about a per topic standard deviation, there's less variance in the 2008 topics. And I mean, we sort of tried to talk about why that is, and we thought about sort of maybe it's because the market collapsed in 2008 and all of the news were the same, or they were all sort of had the negative tone in a similar topic. But those are really just conjectures. So.
So I probably should have mentioned this at the beginning, but when we're actually doing VapoWeb, what's actually happening is we're just minimizing logistic. We're doing logistic regression to try to predict what the output will be. There's a loss function up there on top, And what we see here are the graphs for 2007, 2008 for when we basically line up all the features of all three methods together. And it's nice to see that, in fact, our precision consistently beats out just randomly choosing. And this holds both in 2007 and in 2008. Unfortunately, recall was not so favorable. It should, again, random is up at 0.5. So if you actually look at the F1 score, we do worse than random, but that's life, I guess. I mean, I would love to give you an exact reason on why this is the case. Unfortunately, this ran like yesterday, so I don't have too much to say. Yeah.
Can you see what's the vertical axis again?
Vertical axis. Okay, so what we have here is time, and here is the score. I guess this is recall score, and then on the other one it's precision.
What's the recall score?
Recall tries to estimate. I might get this backwards, but I believe it's the probability that y predicted equals 1 given y true.
Recall is how many of what you actually wanted that you actually got. And precision is how many of what you predicted did you get correct. And F1 is a combination of the two.
Harmonic mean.
Yeah, it's a harmonic.
Yeah. And anyways, that's all I have to say.
So, any other questions?
I'm sure somebody's
So,
got questions.
first of all, thank you very much.